week, I taught you how to destroy functions. Today, I'm going to teach you how to rebuild them. Last week, I asked you what is the derivative. Today, I'm going to ask you something completely different. If I give you the derivative, can you recover the original function? That is integration. Assalamu alaikum everyone, welcome back to Easy Talim. Today marks the beginning of one of the most beautiful chapters in Cambridge A-level mathematics, which is integration. Now, before we start, take a second and think about how far we've come. We have completed algebra, logarithms, exponentials, trigonometry, product, quotient rule, implicit and parametric differentiation, and last Friday we officially finished the differentiation chapter. I'm hoping that you are doing all the exercises in the Cambridge endorsed textbook, which I've been recommending in all my lectures, because otherwise consuming content just for the heck of it is not going to be constructive. Now, today we begin the other half of calculus. So calculus has got two branches or probably three. So limits, differentiation and integration. Limits, differentiation and integration. Okay. Now, by the end of this week, we'll complete integration, and approximately 70% of P3 syllabus will be behind us, leaving numerical methods, vectors and differential equations and complex numbers for the final stretch. So we only have 4 topics left, which are not as big or as lengthy as the differentiation and integration is. Now, let's do a small, very quick recap. Suppose we have y equals to x square. How do we differentiate it? It's very simple. Let's say it is x to the power of 5. Then the differential of this is going to be equal to 5x to the power of 4. Now, what if you have e to the power of 2x? The differential of this, or the y prime of this, is going to be equal to the differential of the power times the exponential function as it is. What if y is equal to sine of 3x? Then y prime is going to be equal to 3 times cos of 3x, right? Now, every differentiation question asks the same thing. How is this function changing? Today, Cambridge changes the question. Now, the question integration answers. Imagine somebody gives you, let's say you have got 6x to the power of 5. Now, this is not a function. This is actually the derivative function. This is the derivative that you have gotten. Now, Cambridge asks you with which function could have produced this derivative. What could y be equal to? Now, notice how different that question is. Differentiation goes forward. You go from y to y prime. Integration goes backwards. You move from y prime to y. So that's integration. That's why another name for integration is also reverse differentiation. Reverse differentiation. Anyway, let me try to explain it to you through a simple analogy. Let's say that you walk into a room. There's broken glass on the floor, a broken vase, water everywhere. You weren't there, but can you reconstruct what happened? Can you put it back in the original form? That's exactly what integration does. Differentiation leaves clues. Integration reconstructs the story. For example, let's say that dy by dx is equal to 10x. What is y going to be equal to? It's very simple. You are going to add one power and divide by the new power. So this is going to be equal to 5x squared. That's very easy. But could y not be, let me change color. Could y not be 5x squared plus 3 or 5x squared minus 8? See, the differential of this is going to be equal to 10x. The differential of this is also going to be equal to 10x. Could it not going to be equal to 5x squared plus ln 2? The differential of this is also going to be equal to 10x, right? Now, suddenly one derivative has produced 3 different functions, and it can produce an infinite number of different functions. This should bother you because it means integration cannot have one answer in the absence of an initial condition or some clue, right? Now, this takes us to the birth of a constant of integration, which is plus c. This is probably the most misunderstood symbol in A-level mathematics. Students think that plus C is something Cambridge invented or mathematicians invented to make life difficult. No, it exists because mathematics demands it. Look carefully. Now, if this is x squared, the result is going to be equal to 2x. If this is y prime is 2x. Now, if you have x squared plus 12, again, y prime is going to be equal to 2x. If this is x squared minus 700, again, y prime is going to be equal to 2x, right? Now, where did those constants go? They disappeared. Differentiation hides constants. Integration has, because see, let's say this is your quadratic function, y equals to x squared plus 2x. So the differential of this is going to be equal to 2x plus 2. At every value of x, this gives us different gradients, right? Now, what does a constant does? So if you add a 2, the graph, this very graph just moves 2 unit upwards. Is still all the curves at those specific values of x are going to stay the same. So if the graph just moves up, I'll show you something. Then at this particular value of x, let's say x naught, this tangent and this tangent are going to be equal, right? So if this is plus 2 or negative 3 or plus 7,000, it doesn't really matter. The gradient function stays the same, right? So we do not know that when we integrate the gradient function back into the original function, where must we put this curve? Whether we put it here or here or here or here. I mean vertically, just vertically. Where are we supposed to put it, right? So unless we are given a condition that this curve also passes through this one particular point, then we plug that in and we get the value of the constant of integration. In the absence of which, if we are going to integrate x squared or if we are going to integrate 2x, we are going to put x squared plus c. We don't know where this c is going to be. So x squared is this, but we don't know whether this graph was passing through the origin. It could pass here or here or here or here. So unless we get a y coordinate and an x coordinate, for example, if we get a coordinate here, then we are going to have a constant of integration here, okay? So therefore, we must write plus c because every constant is possible. Now, I want you to stop saying, don't forget plus c. Instead, say the derivative destroyed the constant when you differentiated a function. So y equals to x squared minus 700. So the dy by dx, it preserved this, gave you 2x, but it destroyed this, right? There was a 0 because the differential of a constant is nothing but 0. So the derivative destroyed the constant. So integration must restore every possibility. Right now, you're not aware whether there was a negative 700 or plus 1 million or negative 1 upon 2 or whatever, right? So in order to restore every possibility, when you are integrating 2x and so if this is the derivative function and you are bringing it back here, so instead of just x squared, you write all the possibilities plus c. We don't know what c is, but it is something, right? It could even be 0. It could even be 0, right? That's understanding and not memorization, okay? I want you guys to look at this plus c like that, so that I'm sorry to say, but if you leave the plus c out of it, out of your integrated function, then one must feel stupid. I feel stupid if I make those mistakes, and I used to make mistakes and get 49 on 50 in my midterms and my A levels. Okay, you don't do that. Don't repeat those mistakes. Now, this symbol is the symbol for. So this is the integrand, right? We put it whenever we want to integrate with respect to x or with respect to y or whatever. Right, whatever the variable is. Now, this is called the integral sign or the integrand, but where did it come from? It is an elongated letter s, right? So s transformed into this, right? And s stands for sum. You'll understand why when we study areas under curves later in the chapter. Today, just remember this symbol means that find every possible original function. Okay, now let's build the first rule. If I ask you to differentiate x4, let's say this is y, and I want you to find out y prime, so this is nothing but 4x cubed. Now, if you have to reverse it, if you have to reverse 4x cubed, So this is going to become x to the power of 4 plus c, because right now you know that you brought it here, but in the absence of this x4, if this is not known, then there are an infinite number of possibilities. It could be x4 plus 1, x to the power 4 plus 1.001, x4 plus or minus 0.9111. Anything is possible, right? So this plus c becomes a necessity. Again, if I give you x7, it produces a differential of 6x, but if I integrate 6 power x with respect to dx, so this becomes x to the power of 7 plus c. This is a must. So can you study the pattern? The power increases by 1, then you divide by the new power. I'm not getting into the details of it because you have, of course, you have done your AS level integration already, so you know it. So this is very basic, right? So I will just write down the rule nonetheless. If this is xn and you are integrating it, so this becomes x to the power of n plus 1 divided by the new power, and then a plus c, which is the constant of integration, and hence n cannot be equal to negative 1. When n is equal to negative 1, there is a special case, and we will learn that when we are doing logarithmic integrations. N to the power n is equal to negative 1 means that we are doing x to the power of negative 1, which is nothing but 1 to the 1 upon x, which is the integral of which, or the antiderivative of which, is ln x, right? And then you put a plus c, right? So just saying, we will do this in further detail, right? You don't have to memorize this. You already know why we do the reverse process, right? So this was discovered, and it was not just, you did not just try to somebody did not just reveal it to you. This is just the antiderivative. Now, an antiderivative was, by the definition of dy by dx, was equal to fx plus h minus f of x over h, limit of h approaches zero, right? We did this. This gave us the rule that dy by d upon of x to the power of n is nothing but x to the power of n minus 1 multiplied by n minus 1, right? So the antiderivative of this is this right here, right? Now, a lot of students make this very common mistake. X power 5 dx integrated with respect to x, they just write x to the power of 6. They just add a power but do not divide by 6. Neither do they put a plus c, right? They did not divide by c. They did not put a plus c, therefore the answer cannot be correct. This is one of the best self checks in mathematics, because because if you differentiate this x to the power of 6, so this is going to give you 6x power 5. There was no 6. Hence it has to be divided by 6 as well, right? Now, if I ask you to evaluate 12x5 with respect to x, so this is going to be equal to, so we can bring this constant outside of the integrand sign. So this is going to be equal to x to the power of 6 upon 6 dx. So this is going to be 2x6 plus c. Okay. Now, let's say I give you to integrate 3x square minus 4x plus 7 with respect to dx. So this is nothing but 3x square dx minus 4x dx plus 7 dx. So this is equivalent to, you bring 3 outside, x square dx minus 4 x dx plus 7 1 dx, right? Just put dx. So integral of x cube is nothing but x square is x cube upon 3. For x it is x square upon 2, and for dx it is just x, and then you put a plus c, right? So this becomes x cube minus 2x square plus 7x plus c. Okay, never try to integrate the entire expression in one step. Linearity is your friend. Do it one by one. Now, examiner tip would be that Cambridge loves expressions with brackets, right? Students panic. However, don't panic. Expand if it makes the integration easier. For example, if it gives you x minus 2, x square plus 5x, and you have to integrate it with respect to x, what are you going to do? You can't do anything. So you just expand it. Turn it into x cube plus 3x square and then minus 10x, right? X cube, yeah, minus 10x, and then you integrate it. So this is going to become 1 upon 4x4 plus x cube minus 5x square plus c. As simple as that. Okay, do not pen, always choose the cleaner route, right? Now let's move on. If you differentiate e to the power of fx, this gives you the same function multiplied by the differential of the power, right, in exponentials. If you have to integrate this, the antiderivative is going to be equal to, you put it back here, but now the differential of the power is going to get divided, okay, and then of course this one, right? So this is the antiderivative of an exponential function. Now if I give you 3e 3x square, if you have to integrate it with respect to x, so this is going to be equal to, you just put it back as it is, 3x square, now divided by the integral of the differential of the power. So this becomes 6x, and then you put a plus c. Okay, as simple as that, right? Now always ask, what does differentiation multiply by? Integration must undo that multiplication. That's why division appears. Okay, now I want you guys to do these questions. 8x 7 dx. Do another practice question, 15x square dx with, and number 3 is 5e 5x dx, and leave your answers in the comment, solve them, and then we are going to resume. So today we have learned that integration isn't a collection of formulas, it's a way of reconstructing what differentiation removed, right? So we are bringing it back to the possibilities of y. I will now move beyond basic reverse differentiation and tackle logarithmic integrals, trigonometric integrals, definite integrals with limits, and most importantly, how Cambridge turned these ideas into full exam questions. That's where integration starts becoming a problem solving tool rather than just a technique. Now let's start with logarithmic integration, right? Now if you have to integrate this, so this is nothing but, okay, before we do that, let's recap how we used to differentiate the logarithmic functions, right? So if you had to apply the differential operator to a logarithmic function, this gave you 1 upon fx times differential of the argument of the logarithmic function, right? Now so if you have it here, now you are going to do, so if you have a linear function, so if you have something of this form and you have to integrate it, this becomes ln function divided by the differential of the argument and plus c. Okay, notice something, this is the only exception to the power rule. If you tried using the power rule, you would divide by 0, right? Provide this only happens when fx is linear, has a power 1, right? If fx is linear, fx has to be linear. This condition must be justified in order to do the logarithmic integration. Okay, that's exactly why Cambridge makes this a favorite exam question, and we will see when we are tackling the exam style questions. Now if I ask you to differentiate ln of negative x, right? So ln of negative x is going to be equal to 1 upon negative x into the differential of so this is going to be equal to 1 upon x, right? So both ln x and ln negative x have the same derivative, right? Ln x also has the same derivative, which is 1 upon x, right? So this is y, and this is y prime, and this is y prime. Okay, now to write one formula that works on either side of 0, we use ln modulus of x plus c is the integral of 1 upon x with respect to x. Okay, this isn't decoration, it's mathematics. Okay, now look carefully. If you have 1 upon 5x plus 2, integral of this, What did I tell you? I said that the denominator is linear, so you put it in the logarithmic function, and then you divide by the differential of the denominator or the argument, right? So that's going to be equal to 5, and then you put a plus c. Okay, this is as simple as that. Now pause the video and solve this one. 1 upon 3x minus 7 dx. Integrate it. I hope you guys have done it and gotten the answer 1 upon 3 ln 3x minus 7 plus c. Always verify, differentiate it, and see if you're getting this result, right? Now, you must never forget this 1/3, right? You must always divide by the differential of this argument, right? Because otherwise it will be taken at it as if you have forgotten the chain rule that still exists, right? Integration always undoes differentiation, right? Now let's do trigonometric integrals. So if this was sine x, this was cosine of x. If this was cosine of x, this was negative sine of x. If this was tan x, this was sec square x. So antiderivatives therefore is going to be equal to integral of sine x is going to be equal to negative cos x. Okay, so if you integrate it, you get this. So if there is a negative sine x, you get a positive cos x. If there is a positive sine x, you get a negative cos x, right? So integral of sine x is negative cos x, and you put a plus c. Integral of cos x is nothing but sine x plus c, and integral of sec square x is nothing but tan x plus c. Okay, always remember, don't memorize, this is just the reverse differentiation. Now don't learn 3 formulas, learn 1 sentence, differentiate backwards. Integration, especially in trigonometry, is just reversal of differentiation. Everything follows naturally after that. Now if you have to integrate 4 cos 4x dx, so the integral of the cos is going to be equal to, first of all, take the constant out, and constant is not this, constant of the function is 4. So you take 4 out, and there's a 4x dx. Now we use, so the integral of cos is sine 4x, and previously we used to multiply with the differential of the argument. Now we are going to divide by the differential of the argument, and there is a plus c. So the answer is going to be equal to sine 4x plus c, right? As simple as that. Now I want you to give me the answer for sine 5x dx. I'm not, comment and comment in the comment section. I'm not giving you the answer. Now whenever the inside contains ax plus b, always ask, the inside means the argument of a trigonometric function or a logarithmic function of, right? So always ask, what would the chain rule multiply by? Integration must divide by exactly that number, right? Because it's nothing but the reversal of that. Now so far we have been putting plus c, right? Now if we were to find definite integrals, if you had to integrate 5x plus 3 with respect to x from 2 to 4, now this is what this is. So first of all you integrate it, so this becomes 5 upon 2 x squared plus 3x, and then you put the limit from 2 to 4. So, and by the way, there is a plus c which gets cancelled when you put the limit. So this is 5 upon 2, 4 square plus 3 times 4 plus c, and then minus, you put 2 now. So this becomes 5 into 4 over 2 plus 6 plus c. So can you see that this c and this c gets cancelled? Hence, in definite integrals, which means when there is a limit, you do not put up a c, right? Because definite integrals ask something different. They don't ask find every possible function. They ask find one number, right? What does this area converge to? This shows an area under the curve, right? Now let's see. Let's do a simpler example. If you're integrating 2x from 1 to 3, right? So this is going to be equal to x square 2x square upon 2, which is nothing but just x square. And then you put the limits 3, 1. So this is 9 minus 1, which is just 8, right? Upper minus lower, right? Now let's do area under the curve. So I'm just doing quickly recapping the entire AS level integration, right? Now suppose y equals to x square. Of course, trigonometric integration and logarithmic integration and exponential different integration wasn't part of your AS syllabus, but we are doing that here. Now, suppose y equals to x square. Now, find the area between x is equal to 0 and x is equal to 2. So, what are they saying? Y equals to x square goes like this. So, this is 4, this is 2, and this is 0. They're asking you to find out this area. This area. This is not a triangle because the area is all the way from here, right? So all of this area, right? Now, so all you have to do is you integrate x square, put the limit 0 to 2 and integrate it with respect to x. So this becomes 1 upon 3 x cubed. Put the limits to 0 to 2. So this becomes 8 upon 3 minus 0 upon 3. So the answer is going to be 8 upon 3 units squared units, right? Now, what's the meaning of the integral? First of all, what does this mean? It is no longer just find the original function. It now means that you add infinitely many tiny strips together. So basically, if you have a function like this, right? Let's say that this is fx. If you have to find out the area from, let's say, from A to B, let's say I break this into infinitely many strips. So these are infinitely many strips, okay? So this is dx, this is dx, right? Very small x, right? So this value is going to be equal to the function value, whatever that is. So if you have to find out this strips area, this is going to be equal to f of x times d of x, right? And how many are these? They start from A and go all the way to B, right? But when you put, so this is n is equal to A to n is equal to B. So basically, so n is the number of these strips. If they are countable, then you put a summation sign. But if they become incountable, if n approaches infinity, just like in differentiation, h was approaching the distance between the two coordinates became 0, almost horizontal distance, then it converted into a calculus, into the first principle differentiation, right? So this now when n approaches infinity, this converts into a summation integral sign, and now you put the limits from A to B. Now these are infinitely many, okay? So every height is y, or every height is fx. Adding infinitely many of them produces the exact area, right? If you add all of these together, right, this produces the exact area, and that is why the symbol originally came from the letter S for summation. And this is summation, and this is sum, right? So this is the continuous form of summation, right? Today we have finally connected the notation with its meaning. Now, I want you to integrate 6x power 5 plus 4e4x dx with respect to x. So now this becomes x6 over 6, and there's a constant, and this becomes 4e4x, and the differential of this gets divided and then plus c. So this becomes x6 plus e4x plus c. As simple as that. Very quick. Now, if I give you this question, 1 upon 2x plus 3 cos 3x, and you integrate it with respect to x, so what is the answer? So this is the logarithmic integration. So ln 2x plus 3 over 2. This becomes the integral of cos is sine. So 3 sine 3x, and then the differential of 3x is 3. You divide it by that and plus c. So it's nothing but half ln 2x plus 3, and then 3 gets cancelled, plus sine 3x and plus constant of integration. Okay. Now, I also want you to integrate 3x plus 1 with respect to x from the limit 0 to 4. It's very simple. Pause the video and then watch this solution that I'm doing right now. So this is 3 upon 2x squared. Integral of 1 is just x. since it's definite integral, we are not going to put a c, and we are going to apply limits from 0 to 4. So this becomes 16 times 3 over 2 plus 4, and minus 0 plus 0 is nothing. So this becomes, 48 upon 2 is 24 plus 4 is 28. 28 units is squared, right? Or you just write square units, right? That's the answer. Now, how does an examiner think about it? Let me tell you how Cambridge thinks, because most integration questions are not testing whether you remember a formula. They even give all those formulas in your MF19. They are testing whether you can recognize which family of functions you're looking at. When you see x to the power of n, you must think of power rule. When you think e to the power of f of x, you must undo the chain rule, right? If you see 1 upon ax plus b, you must think about natural logarithm, because there's a linear function in the denominator and you are integrating it. When you look at cos ax plus b, sin ax plus b, tan ax plus b, or sec square ax plus b, not tan, sorry. So you must think cos, sin, or sec, you must think about reverse trig differentiation, okay? And divide by the inner coefficient, right? Or the inner derivative. The students who score highly don't memorize dozens of rules. They identify the pattern first and then apply the correct reverse process. Now, the main mistakes that students make and lose a lot of marks every year, thousands of marks are lost because of this. They forget this plus c. They forget to divide by this, right? They so whenever they have this, they forget to put ln function, and then they also forget to put c. They also forget to put the modulus, because the argument has to be positive, right? And writing the antiderivative correctly but evaluating definite integrals incorrectly by forgetting upper minus lower, right? So I mean, 1 4, you may forget that you may remember that this is ln x, but then you put 1 here and 4 here, and you mess it all up, because your answer is now going to be equal to minus ln 4. However, the actual answer is going to be ln 4, right? So don't do that. Every one of these mistakes has appeared repeatedly in Cambridge scripts, because the students rush to recall formulas. They're very confident about flipping pages and going to their MF19 instead of asking what function would differentiate to give this. And this is the reason I always tell my students not to bank, not to rely completely on just MF19s. Make sure that you know all of the formulas and all of the applications of these topics by heart, and then MF19 just come to your support and for verification purpose. Today, you have learned much more than a list of integration formulas. I've tried to delve into the basics of this. You have learned how to think backwards, right? Every integration problem begins with one question. If I differentiated my answer, would I get the original expression back? This is your way of verification in exams. If the answer is yes, you're almost certainly on the right track. That single habit will save you far more marks than memorizing another page of notes. Now, in the next lecture, integration becomes significantly more powerful. We'll tackle integration by substitution. Let me write it down actually. So, integration by substitution. We are going to tackle integration by parts. We are going to do more challenging Cambridge applications, and we are also going to do the trapezium rule, which is almost same as this definition, right? You will see. We are going to discuss this on Friday when we are going to conclude this integration chapter. Those techniques are where many students lose confidence, but by building them from first principles, just like we do in all of our lectures, you'll see their logical extensions of what you have learned today. So again, if you found this lecture useful, make sure to like this video. The appreciation means a lot. Like the video, share it with your friend. Don't just hoard the knowledge with yourself. Share it with your friend who's appearing in P3. We are also maintaining a playlist for P1, and then once we are done with these P1 and P3 lectures will be done by the 5th of August. Okay, and after that we are going to move to S2. From the 25th of July we are going to move to S1, because P1 is going to be done by the end of this week. Also follow Easy Talim on Instagram, and also subscribe to this channel. On Instagram, we go by the name of Easy Talim. We are uploading a lot of good content there as well, so you should definitely go and follow that page. If you do have any questions, leave those in the comments or on WhatsApp. Our WhatsApp is +92 329 3028 485. Just save it in any case, and I'll address common difficulties in my upcoming lessons. I'll see you guys in integration part 2 on Friday. Until then, keep thinking like a mathematician and not as a memorizer. Take care. Allah Hafiz.